Today's seminar is going to focus on functions, domain, and range. And the goal for this lesson, or our I can statement, will be I can identify a function through many representations and write a function rule. So those will be the two things that we're focusing on today. At this time, what I'd like you to do is pause the video, write the title of this lesson in your notebook, along with the goal at the top of the page in your notebook. Alright, so today we'll have two different foldables that we're looking at. The first one we'll look at is one that identifies functions from other things that aren't functions, as well as representing functions as rules, tables, and graphs. So just how to identify them and then how to represent them in different formats here. So let's go ahead and start off with this foldable here. So when you get this, what it will be is a full sheet of paper. And what you'll need to do is fold your sides in. And they might overlap. It's not perfect, so don't worry if that happens. And then what you need to do is just cut halfway so that these little flaps open. So let's get started. Let's first look at what determines what a function is and what determines what a function isn't. Okay, so functions, we're going to have a definition in here. So open this side up, and also the other side will open up as well. Okay, so we're looking at functions on the left-hand side. So in order for a relation to be considered a function, each member of the domain X, so your domain is your X values, it must be paired with only one member of the range, or our Y values. So if we're referring to the domain and range, when referring to domain, it's just your X values, and referring to range, it's just your Y values, whether it's from a set of ordered pairs, a table, or anything that follows suit with an X and Y variable. And for something to not be a function, so it says, if a member of the domain, or your X values, remember, is paired with more than one value in the range, Y, then it is not a function. So if you have an X value, so let's say 2, going to both 3 and 5 in your Y values, then it's not a function because each input, which we'll get to later, must be paired with exactly one output. So what I do is make sure that you get these written in your notebook. I'll just zoom out here a little bit so that they both fit. So if you'd want to pause here and write these down, now would be a good time to do that. Okay, moving on. So we have many representations of functions, and they are ordered pairs, tables, mapping diagrams, and from a graph. And there's different strategies we can use with each of these in order to determine whether or not they are functions. So let's start with ordered pairs. And let's determine why this is a function. So we have the set of ordered pairs here. So we have 4, 6, 7, 2, and 5, 1. So the reason why this is considered a function is because every X value is paired with a different Y value. So each input, or X value, has exactly one output. So we'll say every X is paired with a different Y. So you can see 4 is paired with 6, 7 is paired with 2, 5 is paired with 1. There isn't a repeat of an X value going to a different output, so we're okay here. This is considered a function. Now on the other hand, over here we have 8, 3, 9, 5, and 8, 6. So This one is not considered a function because we have 8, which is an input, and it's going to both 3 and 6. So that breaks that rule of what a function is, that each input has exactly one output. Or each number in the domain, or x value, is paired with exactly one number in the range. So we could say a member of the domain is paired with more than one member of the range. And what we could say here is that 8 is paired with 3 and 6. So that would be a representation with ordered pairs. So once again, we got to remember that key term here, that each input is paired with exactly one output. And here we don't have that because 8 goes to both 3 and 6, like I said. All right, so then let's move on to the table representation. And let's look at both of these. So this one here on the left-hand side is considered a function because every x is paired with a different y. Okay, so 3 goes to 9, 4 goes to 9, 5 goes to 9, 6 goes to 9, and 7 goes to 9. It's okay if the output or your range, if all of those numbers are the same. It's not okay, however, if you have the same number in the domain or your x values that's the same. So let's say I had 2 3s going to a different number. Well, that wouldn't work. But when the range, if the range is the same, that's okay because it still fits the definition. Each input is paired with exactly one output, and this is the case in that one. So let's look at our not a function side. So we have 2 going to 3, 4 going to 6, 4 going to 9, 6 going to 12, and 8 going to 15. So this is similar to what I set up here on the top, that a member of the domain is paired with more than one member of the range. So a member of the domain is paired with more than one member of the range, and in this case, we would have 4 is paired with 6 and 9. So since 4 maps onto both 6 and both onto 9, it's not considered a function because it doesn't meet the definition. This topic really just comes down to the definition. Let's look at a mapping diagram here real quick. So on your entry slip, you're asked to make a mapping diagram. This is what those look like. So you have your x values or your domain and your y values range, and you use an arrow to point where they go. So here again, so this is a function because every x is paired with a different y. So every x is paired with a different y. 1 goes to 5, 2 goes to 10, 3 goes to 15, 4 goes to 20. You don't have one x value going to two different y values. Now on the not function side, we have 2 going to 10 and 20, 4 going to 30, 6 going to 30, and 8 going to 40. So the problem here is that 2 goes to 10 and 20 in this case here. So not a function, because just like above, and you can just write this down, a member of the domain is paired with more than one member of the range. So I'm just going to say 2 is paired with 10 and 20. So that makes it not a function. And last but not least, we can have functions represented as graphs. And we have something like, if we're just given the graph of something, we have another test that we use, and that's called the vertical line test. So how we can think about this is, if I were to take something that's vertical, so let's say my pen, and I run it across this graph, at no point will my pen, or whatever I have, intersect at more than one point on this graph. If my vertical line intersects at more than one point at one time, then it fails the vertical line test and it is not considered a function. So this is a function because it satisfies the vertical line test. Now when you're given a graph and it asks you whether or not it's a function, just do the vertical line test. It's going to be the quickest way to decide whether or not you have a function or not. So then over here we have kind of a parabola on its side, and what happens when I run my pen across this is that I end up having my vertical line intersect the graph at two different points. So it's intersecting at the top here and at the bottom at the same time. So that means my x value of 3 is intersecting y in two different spots, and that's not okay. That doesn't satisfy a function. So over here what I would write is it does not satisfy the vertical line test. So this is just a quick representation of the different ways that we can see functions and determine whether or not they are or are not functions. So make sure that this gets put into your notebook so that you can refer to it whenever you're working with functions. So now what we're going to do is just switch over to our other foldable that we'll have, and that's on representing functions. So actually writing the rules from tables and graphs. Okay. So just some information here for you real quick. We'll just recheck this, go over this, because we kind of defined this on the last foldable that we had. So here's just kind of a nice chart. So x values, that's your domain. If they ever ask for the domain, it's just all of your x values. This is also going to be your input, which we'll get into once we get into looking at tables. Your x is always your input. What are you putting into whatever equation it is or whatever function it is? And these can stand independent because we know these. We define these. We pick our x values. Y is considered the range, so if they ever ask you for what's the range, you just need to list all your y values. That's considered your output, so after we put in the x values we chose, the y, or the range, is what we'd get out. So whatever function we would put that into. And these are dependent because they depend on the x values that we put in. Now I had kind of talked about a relation before, Relations and functions are related in a way. A function is just a special type of relation, and we define a relation as a set of ordered pairs. So if we just had a group of ordered pairs, that's considered a relation. What makes a function a special type of relation is that it's a relation in which every member of the domain, or your input, or your x values, is paired with exactly one member of the range, or your output and your y value. And I had mentioned that earlier on your other foldable. So what we're going to do now is look at a couple different representations here and decide whether or not they are functions. Okay? So make sure that you get this top part filled out. If you need to pause the video here, now would be a good time. Alright, so keeping the definition of a function in mind, let's move forward here and tell whether or not these are functions that we have listed below here. So let's look at letter A. Remember, we're seeing if each input or x value or each number in the domain is paired with exactly one member of the domain, or I'm sorry, with the range, which are your y values. So if we look here, 1 goes with 3, 2 goes with 4, 3 goes with 7, 4 goes with 13. In this case, I would say yes, that this is a function because each x value is paired with exactly one y value. So yes. And we could say yes. Every member of the domain remember that's your x values, is paired with exactly one member of the range. So we can say that yes. Okay, give B a shot, remembering what the definition of a function is. So give that one a shot and decide whether or not it's a function. And if it is, tell why. And if it's not, tell me why as well. So, in this case, you should have decided that no, this is not a function because 2 is paired with both 6 and 7. So we can't say that it is a function because we have the input of 2, so a member of the domain, is paired with two different numbers in the range. So 2 goes with 6 and 2 goes with 7. That automatically invalidates it as a function, so we can only consider it a relation. Now, part C and D, we have a graphical representation of a function or possibly not a function. So we had, on our other foldable, we had decided what we need to use when it comes in terms of that. And if you remember, we have to use the vertical line test here. So looking at this first one, if I were to run a vertical line across here, it should only intersect the graph or the representation at only one point at all times. But if I do that, what I notice is, if I drew a vertical line through this spot here, it would go through two different points. And that's not okay. Same thing happens here. If you want to draw that in to show yourself that, you can absolutely do that. So in two different spots, this fails the vertical line test. So no. We could say fails the vertical line test. Try the next one on your own and decide whether or not it is a function. So in this case, yes, this one is a function. passes the vertical line test. So if I were to run, like I said, my pen across here, it's only going to touch each one of those points on this function once. It never intersects anywhere twice at the same time on this whole thing. So just think of running an imaginary line across the whole thing, or use your pencil, ruler, whatever, in order to test the vertical line test. Like I said, it's probably one of the quickest ways to test whether or not something is a function. Okay, moving on. So we're going to look at a graph now here, and what it says here is make a table and graph the function. So what we're going to do, and I'm going to use a vertical XY table. I just think that works a lot nicer. So X, Y, I'm going to make a table. So that's the first thing we need to do, and once we do that, we need to graph it. So what this is telling me is that my domain, or my x values, I'm going to copy over 0, 1, 2, and 3. Those are my independent variables. I know what those are. Now I'm going to find my range, or my y values, and those depend on what we put in for x, or substitute in for x, within this equation here. So if I put 0 into here, I'd end up having 3 times 0, which is 0, and then I would do 0 minus 4, which would be negative 4. If I do the same thing for 1, 3 times 1 is 3, 3 minus 4 is negative 1. So you see you're just substituting your values of x into here in order to get your y value. So if I put 2 in there, 3 times 2 is 6. 6 minus 4 is 2. If I put 3 in there, 3 times 3 is 9. 9 minus 4 is 5. And what it asks me to do here then is to graph it. So remember, in an ordered pair, it's x comma y. And we need to plot these points. So 0, that means I'm not moving anywhere on the x, and I'm going down 4 spaces. 1, 2, 3, 4. So that's where my first point is. It's kind of hard to see that, but you should be able to plot it. My next one would be 1, so I'm moving 1 to the right on here, and I'm going down 1, plotting that point. 2, 2 would be going 2 to the right, and then up 2. And then 3, 5, I'd go over 3 and up 5. So it should be 1, 2, 3, 4, 5 here. And in this case, this one is going to be a function because we could take the vertical line test, and at no point does my marker intersect at 2 different places at the same time on this function representation. Now one other thing that I want you to do here is to write down the range. And the range simply is all of your y values. So we would just write negative 4, negative 1, 2, and 5. And if we ever had a repeated value, like let's say we had 1 going to 2 and 2 going to 2, we would only write 2 down once. We don't need to list it twice. And if you're asked to write down the domain and the range, it's simply writing down your x values for domain and your y values for range. Simple as that. I want you to go ahead and pause here and try the second one here. Remember, you want to draw a table and then graph the function and write down the range. All right, so you should have tried this one. I'll go ahead and run through it quick. So my x and y, I have 0, 2, 4, 6. Should be some easy numbers to work with here. So if I put 0 in, 1/2 times 0 is 0, plus 1 is 1. If I put 2 in, 1/2 times 2 would be 1, plus 1 is 2. If I do 4 in there, 1/2 times 4 is 2. 2 plus 1 is 3. If I put 6 in, half of 6 is 3, plus 1 is 4. Then I need to plot these points over 0, up 1, over 2, up 2, over 4, up 3, and over 1, 2, 3, 4, 5, 6, up 4. So we should have that. And then if I were to list my range, that's just all of my y values. So draw my curly bracket, 1, 2, 3, and 4. And that's it. And both of those would be considered functions that we just did because, like I said, they'd pass the vertical line test. Would only intersect at one point no matter where I go across the board. And last but not least, what we're going to do is what we've been doing for our Tough Pattern Tuesday, writing a function rule for our functions here. So if you remember, we looked at this in a couple different ways. We try to find what's happening between the x values and the y values, and then try to find where we can determine if something's added or subtracted after that. So if I look at this one here, these are changing by plus 1 each time. And my x values are also changing by 1 each time. This is exactly what we do in Tough Pattern Tuesday. Now, in order to determine what I'm multiplying by, I need to look at how my y is changing over my x is changing. So y over x. And in this case, so this is increasing by 1 each time. So it would be 1 over. My x's are changing by 1 each time. And we can just call that 1. So we can say that y equals 1x, or we could just put x by itself. Now here's a cool trick that I've kind of explained when we're doing Tough Pattern Tuesday, is to find where y equals 0. And where y equals 0, whatever that x value is what you're adding or subtracting after this here. Okay, and later on this will be known as our y-intercept when we get to graphing lines. The first part was known as our slope. So if I look for my 0, I have 0, 3. So I know that I need to add 3 since it's a positive 3. So my function rule for this one is y equals 1 times x plus 3. Now, the good way to test this would be to take a x value, plug it in, and see if we get our y value. So, if we did, or did I put the wrong thing here? Maybe I don't have, hold on a second. So if I put that in there, this isn't coming out quite right. Well, we'll come back to that one here in a second. I'll have to take another peek at that. But for this one, that's what it should, 1 times 2, no, that wouldn't give me negative. We need minus 3 here. So this should be plus and negative 3. So we don't quite have the right rule here. So we'll go with that. What I'd like you to do, try letter B and letter C and see if you come up with the right function rule. So you can pause the video. All right, so let's take a peek at this then. My y values are changing by a value of 6. Say, is that 9? These are changing by so those are actually changing by 1 each time. Because if we look plus 2, plus 3, there's a shift of 1 between there. And these are changing by 3. So we would want to look at our y over our x, and if I did, I should get 3 over 1. So then what I'd say is y equals, and then whatever's here needs to go next to your x. So I'm just going to say 3x because 1 isn't really necessary. And then I'm going to look where my 0 is. So where y equals 0 is what I need to put in. So we're not actually, we could say plus 0, but in this case we could just do 3 times x. So if we plug these in, 3 times 0 is 0, so that works. 3 times 2 is 6. 3 times 5 is 15, 9 times 3 is 27. So that's working there. And really, I guess with this one, I should have my kind of secondary here. So we can see that this is changing by 3 each time, and I could do up here as plus 1 as well. Now, the reason this looks goofy is because we skipped numbers in here. So really, if I had put 1 in here, 2, 3, 4, all these would change by 1, and all these y values would change by 3. So sometimes you have to dig a little deeper within these to figure that out. So let's look at C then. So 2 to 5 would be plus 3, 5 to 8 would be plus 3, 8 to 11 would be plus 3, and the top is all changing by 1. So if I do my y over x, I'm going to be left with 3 over 1, which I can say is just 3. So y equals 3x. Let's find where my y equals 0. I'm sorry, where my x equals 0 is what I should say. So x equals 0 here. So where my x equals 0 is what I'm adding. I'm sorry that I said y before. It's where your x equals 0. So, and I see that my y value there is 2, so I add 2 here. So 3 times 0 is 0 plus 2 is 2. 3 times 1 is 3 plus 2 is 5. 3 times 2 is 6 plus 2 is 8. 3 times 3 is 9 plus 2 is 11. That one works out. Let's go back up to letter A real quick so that I can clarify what's going on here. So if I were to move backwards on this table, I would have 1 and then I would have 0. And if I moved backwards at 1, I'd be at negative 2. And at 0, I would be at negative 3. So since x is 0 here, wherever your x is 0, whatever number corresponds with y should be added or subtracted at the end. In this case, it should be minus 3. I'm sorry for that confusion, but wherever your x value is 0, you put that y value in order to add that to the end or subtract it. So in this case, x is 0, y is 0, we add 0. In this case, x is 0, y is 2, we add 2. So that's the correct representation of that. Once again, I'm sorry for the confusion. Then, last but not least, let's take a peek at our last part here. So if we have a graph, can we write a function rule from it? Well, yeah, we can. And what I would stress is drawing a graph here. So here's how you're going to have to, or I'm sorry, here's where you're going to have to understand how to write ordered pairs. So my x value in this case would be 0. My y value would be 1, 2, 3, 4, 5, 6. This would be x is 1. This would be 7. So we'd have 2, 8, and 3, 9. Now from here, what we can do is the following. We can look at our change in y's. So we know this is a plus 1. With 7 to 8 is plus 1. 8 to 9 is plus 1. These are changing by 1. Now remember, to find that first part that's next to x, which is really our slope, is going to be y over x. So we know that, so our change in y is 1, and our change in x is 1, so that's 1. And like I said, so we'd have y equals 1x. Now we're going to find where x is 0, and in this case, x is 0 here, and our y value is 6. So we'd add 6 to that. So our equation here is y equals x plus 6. Now we can plug those in again just to test it. If I put 0 in for x, 1 times 0 is 0. Add 6, I get 6. That worked out. If I put 1 in, 1 times 1 is 1. 1 plus 6 is 7. 1 times 2 is 2. 2 plus 6 is 8. And 1 times 3 is 3. 6 plus 3 is 9. What I'd like you to do now is to finish B by yourself. So pause the video here and give it a shot. And I'll go through it here in a second. Okay, so my first point is, 4, 0. Second point is 5, 2. Third point would be 6, 4, it looks like. And my last one would be 7, 1, 2, 3, 4, 5, 6. 7, 6. Let's look at our change in our y's. Plus 2, plus 2, plus 2. These are changing by 1. If we do our y over x, we get 2 over 1, which is just 2. Now we might have to work backwards here a little bit in order to figure out what our y-intercept is going to be. So first and foremost, we would have, and I'm going to write this above here, y equals 2x, because 2 is our slope. 2 over 1 is our slope. Let's work backwards in our chart until we get to 0. So if I went to 3, I should be at negative 2, because I would just subtract 2 the other way. If I would get to 2, I would be negative 4. If I'd get to 1, I'd be negative 6. 0 would be negative 8. So we'd have minus 8 here. And if we were to extend this line, we would find that somewhere down at negative 8, or down at negative 8 on your y-axis, your up and down vertical axis, this would intersect. So this is how you write function rules from graphs, from tables, and determining whether or not we have a function or not. So make sure that both of these foldables, like I had mentioned, get put into your notebook, as you'll need to refer to them when doing assignments. And just as a repeat then, our goal for the day, remember, we focused on functions, domain, and range. And our goal was, and our I can statement is, I can identify a function through many representations and write a function rule. As always, if you have any questions, please feel free to talk to me.